Let's take a look at another example of a related rate problem. Take a moment and read this over. Anytime we have a related rate problem, it's going to be really helpful if it's geometric to try drawing a picture. So what's going on here? We have a vertical wall and we have a 10-foot ladder that is resting along this wall. X is going to be the distance of from the bottom of the ladder to the wall. So this distance here is going to be called X. Y is going to be the height of the ladder against the wall. Okay, and so let's think about what's happening. We're going to see that the bottom of the ladder slides away from the wall at a constant rate of 3 feet per second. Okay, so our X is going to be increasing. Nope, our X is increasing at this constant rate of 3 feet per second. And what we'd like to know is what's going on with the top of the ladder. So the top of the ladder, because this is 10 feet, the top of the ladder is going to be sliding down the wall. We can see that our y value is going to be decreasing. But what about dy dt? What we'd like to know is dy dt an increasing function? Are we speeding up? A decreasing function? Is it slowing down? Or is it a constant function? After all, the x dt is a constant function, 3 feet per second. So I'd like you to think for a moment about this situation and make a prediction. Do you think dy dt is going to be increasing, decreasing, or a constant? So I have this grid paper to help us organize the information that we've got. So if we think about what's varying, x is varying, and so is y. And the constants that we have, well, we know 10 is the length of our ladder. Okay. X was the distance to the wall, and y was our distance to the ground. Okay. What we're interested in knowing about is dy dt, the rate of change of y, our height from the ground. And let's think about some of the things that we know. Okay. So when we're looking at what we know, what I'd like us to try and do is come up with a relationship between the variables that we see. We're interested in finding dy dt kind of overall if dx dt is equal to 3 feet, always. Okay. So some of the things that we know here, we have a relationship between x and y, which is that they are sides on a right triangle. And so we can relate them with this equation that x squared plus y squared is equal to 10 squared, or 100. Okay. So what we're going to do is take this equation that relates the variables, and then we're going to differentiate it with respect to t, because x depends on t, and so does y. Okay. So we have x squared plus y squared equals 100. And what we're going to do is differentiate with respect to t. So using the chain rule, we have that the derivative of x squared with respect to t is going to be 2x times dx dt. And the derivative of y squared with respect to t is going to be 2y dy dt. And the derivative of 100 with respect to t is equal to 0. So what we want to know is dy dt. And what we know is that dx dt is going to be equal to 3. So we can solve for dy dt in terms of x and y. Okay, so I'm just going to move the other pieces over. So we have that 2y dy dt is going to be equal to negative 2x times 3, that's dx dt. And so dividing both sides by 2y, we find that dy dt equals negative 3x over y. This negative sign means that our distance to the ground is decreasing. And let's think about, as y gets smaller, what happens to dy dt? Does it go up? Does it go down in terms of its size? So our y values are going to be getting smaller. So smaller y means that the size of this fraction, 3x over y, gets bigger. And so what's going to happen is that as this ladder base slides out, the top of our ladder actually is going to speed up as it moves down the wall. All right, and we can take a look at a specific snapshot in time. It says when the top of the ladder is 6 feet above the ground, how fast will it be sliding down the wall? Often, when we're interested in this kind of snapshot in time, it helps to return to our picture that relates our variables. We have x, which is our distance from the wall. We have our ladder length of 10, and our y value here is equal to 6. So we're able to solve for x, which we are interested in because it shows up in our formula for our rate of change of y. So we have x squared plus 36 equals 100. And so x squared is equal to 64, and x is 8. At this particular moment, so our dy dt will be negative 3 times our x value over our y value, which was 6. So this is going to be negative 24 over 6 feet per second, or negative 6 feet per second. Okay, great.